Hey everyone, welcome to The Explainer. I'm so excited you're tuning in because today we're diving straight into something that is just incredibly powerful. We're going to master section 11.2 of your syllabus, which is all about plotting linear graphs. Now, if you've ever stared at a bunch of algebraic equations and felt like you were looking at some completely foreign language, well, this explainer is going to change the game for you. We're going to take all those abstract numbers and make them perfectly, beautifully concrete.
So, I want you to ask yourself, how exactly do you make invisible math visible? It sounds kind of like magic, right? But honestly, just think of algebra as a secret code. Sitting there on a page, an equation is just a bunch of numbers and letters. It has a story to tell, but it's totally hidden. So today, we're going to translate that code into a physical picture. We're literally building a bridge between the numbers we calculate and a tangible line we can actually point to.
Now, this translation trick isn't exactly new. We actually have to jump back to 17th century France for a second to meet a pretty brilliant guy named René Descartes. He came up with a massive game changer, the Cartesian grid. This invention let us map mathematical relationships right onto a piece of paper. And yeah, we still call them Cartesian coordinates today in his honor. It was this huge, revolutionary moment because suddenly, math wasn't just stuck in our heads anymore. It was something we could actually draw.
All right, so here is our game plan for today. We've got a super straightforward 5-step recipe to conquer this. First, meet the linear function. Second, constructing a value table. Third, calculating your coordinates. Fourth, the Cartesian grid. And finally, step 5, connecting the dots.
Let's jump right into step 1, meet the linear function.
You know, you really can't bake a cake without knowing your ingredients, and you definitely can't plot a graph without understanding your function. This is the exact transformation we're going for. We start with the abstract, an algebraic equation like y equals 2x minus 1. To most people, that's just symbols. But our concrete goal? A perfect straight line on a graph. That equation is actually just a set of instructions telling us exactly how to draw that line.
So what really makes a function linear? Basically, a linear function is just a function in the form of y equals mx plus c. The m and the c are just placeholders for numbers. Our source material gives us a couple of great examples, like y equals 2x minus 1 or y equals 8x plus 4. Whenever you see an equation in this exact format, no squared numbers, no crazy powers on the x, you know for an absolute fact that your final graph is going to be a straight line. Just think of the function as a little mathematical mixer. Whatever number we toss into it, the rule mixes it up and spits out the exact coordinate for our line.
Moving right along to step 2, constructing a value table.
I want you to think of this table as your workspace or your prep station. We've got a top row for our x inputs and a bottom row for our y outputs. And notice how we've pre-selected standard x values ranging from -2 all the way up to +3. We do this because it gives our function a really solid test across both negative and positive territory. We're basically asking the math, hey, what happens when x is -2? What about when it's 0? This table just keeps all those answers totally organized for us.
Step 3. Calculating your coordinates.
Let's actually walk through the mental math together, using our rule y equals 2x minus 1. First up, let's pick x equals 3 from our table. Following our rule, we just substitute that 3 right in for the x. So we multiply 3 by 2, which gives us 6. Then the rule says subtract 1. 6 minus 1 leaves us with 5, meaning when our x input is 3, our y output is 5. Pair them up, and your resulting coordinate is the point 3, 5. It really is that straightforward.
Now let's make sure the rule holds up by testing a negative number. Let's grab x equals -2. We'll run it through the mixer, multiply -2 by 2, and we get -4. Now subtract 1. -4 minus 1 drops us further down that number line to -5. So our coordinate pair here is -2, -5. The algebraic rule never ever changes. We're just carefully substituting the numbers and solving.
And if we repeat that exact same process for all our chosen x values, look at what we get, a totally complete table. For every single x we put in, we found its matching y. -1 gave us -3, 0 gave us -1, you get the idea. We now have this fully organized set of coordinate pairs just waiting to be mapped out. We took that abstract equation and turned it into hard, concrete data points.
Which brings us to step 4, the Cartesian grid.
We've mixed our paint, so now we need our canvas. Picture a grand cross perfectly centered on your page. That horizontal line running left to right, that's your x-axis. The vertical one, running straight up and down, is your y-axis. Right in the absolute center where they cross is the origin, sitting perfectly at coordinate 0, 0.
When you plot the coordinates we just found, you always read them as x, y. You crawl along the horizontal x-axis first, and then you climb or fall along the vertical y-axis, over and then up or down.
Before you start throwing points onto your page, though, I have to give you a pretty crucial warning straight from the source. Scaling absolutely matters. Let's look at that other function we mentioned, y equals 8x plus 4. If we test our x value of -2 in this one, well, 8 times -2 is -16, plus 4 gives us a y value of -12. If you're just counting by ones on standard graph paper, -12 is probably going to run right off the edge of your desk. So always check your table of values first, spot your biggest and smallest numbers, and choose a scale so everything fits comfortably on your canvas.
And now for the grand finale. Step 5. Connecting the dots.
Our source sums this up perfectly. You can use these coordinates to plot points on a grid. You can draw a straight line through all the points. This is that awesome aha moment. Once you've mapped your coordinates onto the grid, like 3, 5 and -2, -5, you just grab your ruler. If you did your mental math right in step 3, that ruler is going to line up perfectly straight across every single dot. When you connect them, you've successfully transformed that secret algebraic code into a visible, continuous straight line. You just brought the math to life.
So we've totally mastered the steps today. But before we wrap up this explainer, I want to leave you with something to think about. Is there a way to predict where this line will cross the axes before you even bother making a table of values? What if that little y equals mx plus c formula is hiding even more secrets, like shortcuts for gradients and intercepts right out in the open? Well, that is a fascinating shortcut we'll be tackling in our next session. Until then, grab some graph paper, try out a few linear functions yourself, and have fun making that invisible math visible.